Hi, everyone. Time for a little more chemistry. Let's look at reversible reactions. Now, these are reactions that can go forwards and backwards. New twist. So this is also called chemical equilibrium. We'll explain why it's called an equilibrium in a minute. But first of all, reversible reactions. That's simply reactions that take reactants, make them into products, and then the products turn around and return back to reactants. The forward direction, of course, is the one we're more familiar with. You start with reactants, they change into products. But now the backwards reaction says the products, they become the reactants and they go backwards and make the old products, which were the reactants. And turns out this is much more common than you might think. So picture says 1,000 words. Let's take molecule A, molecule B. Do a reaction, go forwards, and make it into molecule C. That's the normal forward direction. But now it says that, hey, in some cases, the product you just made, molecule C, that can fall apart. That can go back. If you spin around, you can say molecule C now acts as the reactants and can return back to A and B. I guess as you draw this reaction, it looks like the products. Yeah, it can go back and forth. So we're going to use a double-headed arrow, and you can get all fancy like this one, or you can just say, or just draw an equilibrium arrow, reversible reaction arrow like this. And you can say, hey, sometimes these two travel across the top arrow, make products, but then sometimes the products travel across the bottom arrow and return back to reactants. It happens. If this is happening, if you have an equilibrium reaction, a reversible reaction, it happens continuously. It doesn't stop. It kind of looks like, from the outside looking in, it looks like things have reached a resting point. It's really reached an equilibrium point. The reaction continues. The reagents A and B change in the C, but then C says, nope, we're going to go back to A and B. It just happens that once it reaches this equilibrium point, this place where nature says, yeah, we're good, you guys can go back and forth as you want, the rate or the speed of the forward reaction is the same as the reverse. This is kinetics, so review that in our previous video about kinetics, rates of reactions. But it just says, hey, the rate, the speed at which A and B becomes C is the same at which C turns back into A and B. At this equilibrium point, you're not changing the numbers of A, B, and C. If you look at just the forward direction, yeah, the molecules A and B decrease as they turn into C, and C increases. But guess what? Same time somewhere else in the beaker, there's another molecule C that just split into A and B. So the same time there, A and B at one part of the beaker changes to C, a different region in the beaker, molecule C changes to A and B. And remember, a reaction isn't just, one molecule of A, one molecule of B. It's Avogadro's number, 6.022 times 10 to the 23rd. Lots of molecules, so there's lots of A's, lots of B's, and lots of C's. And we're saying equilibrium. As the reaction goes forward, it also goes backwards within that container, the beaker, or whatever. The other thing you can say is that the free energy change, the delta G, is 0. Remember we said delta G is negative for a spontaneous reaction, a reaction that wants to go all by itself. And if delta G is positive, you said it's non-spontaneous, but the reverse reaction is spontaneous, meaning it can go backwards all by itself. And at the special case where G is neither positive nor negative, it's actually equal to 0, then you're spontaneous in both directions. Molecules A and B can make products, and molecule C can make reactants. They can go back and forth at equilibrium. Maybe we should give a little context here. It turns out reversible reactions are much more common in nature than the normal, what we think is normal forward reactions or one-way reactions or completion reactions, right? We talked about, hey, go take, let's balance an equation, and maybe it's a precipitation reaction. So take reagent A and B, which are aqueous, mix them together, you make a solid. Yeah, it all converts. Well, that's not exactly true. After you make some of the solid, a little bit of the solid can redissolve into the individual ions. And then those individual ions can stick together and form solid, and back and forth it goes. It's actually an equilibrium reaction. Maybe more relevant is that most of the biochemical reactions in our bodies are actually reversible reactions. So if you even think about what makes up a cell, you got DNA in there, you've got RNA, you got proteins, and what happens when a cell dies? All those molecules break down, and the body uses those building blocks to make new cells. Or how about just eating food? Look at a nutrition label, and on the label it says there's a certain amount of carbohydrates and proteins and lipids in there. And so eat like some celery or some lettuce, whatever, an avocado comes from a plant. There's lots of carbohydrates and proteins in there. And then we digest that. We break all those down, break down the carbohydrates and the sugars, break down the proteins and amino acids. And then what's our body do? Make new carbohydrates and new proteins out of those. So it's totally reversible. Take a protein, break it down amino acids, take the amino acids, make new proteins out of it, and back and forth we go. Makes life possible. Reversible reactions. Kind of important then. This balancing point, right? We got A and B becoming C, C going back to A and B. Turns out nature doesn't really play fair. She doesn't say, okay, at the balancing point, we have the same number of reactants as products. No, we're not. In fact, sometimes nature will say, let's just swing all the way over to the product side, like a plant growing like a strawberry plant producing a strawberry. The plant is just doing photosynthesis to make glucose, puts that glucose together to make starch, and builds up a big strawberry, trying to drive it all the way to products, carbohydrates, let's say. Strawberries made of starches and sugars, carbohydrates. We eat that strawberry, our body breaks it all down. We're trying to reverse it, go all the way back to glucose, and then, hey, let's get some energy out of that. Glucose is actually blood sugar. Let's break that down to carbon dioxide and water, really break it down, and all the way to completion. And then photosynthesis says, well, let me take that carbon dioxide and the water, and with a little sunlight, go make glucose again, reverse it. And it turns out that equilibrium, you usually do not have the same number of reactants as products. Nature will find a way to drive the reaction to one side or the other. It's what makes life possible. Okay. Let's go a little more simple. Let's not talk about photosynthesis and carbohydrates and proteins, even though that's interesting. We'll save it for another day or another class, actually. Let's just look at the simple reaction here. Nitrogen dioxide, 2 molecules of NO2 can change into 1 molecule of dinitrogen tetroxide, N2O4. And hey, that N2O4 molecule is not very stable. It can break back down into 2 molecules of NO2. And so I got the same set of molecules, NO2, N2O4, in these sealed flasks. And actually, this is a time-lapsed set of pictures here. It's the same flask. So someone filled up the flask with a little bit of NO2, a little bit of N2O4, let it wait. This is in a beaker of water at room temperature. That's not a beaker, it's some type of evaporating dish, whatever. It's a water bath, keeping this flask and the gas inside at a constant temperature. And if you go look inside, turns out at room temperature, nature says my balancing point is I like lots of NO2s. And through different experiments, we'll discover that NO2 is actually brown and the N2O4 molecule has no color. Okay, so at the sealed container, room temperature, nature says Okay, yeah, the reaction goes back and forth, back and forth, back and forth, but we're going to end up at our balancing point, our equilibrium point, where we have a lot more NO2s. Cool, we say as scientists, that's nature's prerogative, but you know what? Let's kind of mess with things. Let's cool this down. Let's add some ice to the same system, not changing any of the reagents or anything. And slowly you'll start to see the flask lighten up in color. Where's that brown color going? Well, the forward reaction starts accelerating as you change the temperature. Lowering the temperature causes more NO2 molecules to collide to form N2O4. And then the N2O4 at cold temperatures is not as unstable. It's a little more stable and sticks around. So if you look in here, there's a lot more N2O4 molecules, which they don't have much color. There's still some NO2 molecules, so there is a light brown tint to this because of the NO2 molecules. And it doesn't stop. It continuously goes back and forth. So we might see, hey, warm solution going to cold. Ooh, we'll see the color fade. We know something's happening, and it's this. The NO2s are becoming more N2O4s that don't have my color. And eventually the color change will stop. Keep ice in here, keep it cold, it won't change color anymore. But if you can zoom in and look at individual molecules, like maybe you look at this N2O4 molecule, you might see it split apart. It's like, wait, it just made two NO2s? Shouldn't that make the flask dark in color? Well, at the same time one of these is splitting, somewhere else, there's two NO2s that collide to make a new N2O4. So even after there appears to be no more changes, the color's constant. If you zoom in and look at the molecules, they're still reacting. Reactants becoming products, products becoming reactants, but they happen at the same rate, so there's no net change in the quantity of reactants or products. Cool. That's an equilibrium reaction, a reversible reaction. Top of the page, please. Okay, let's look at another one here. Let's go here. Move this over there. Okay, so we're going to look at the reaction that can make ammonia, NH3. It turns out to be a reversible reaction. You take one molecule, the recipe. The recipe says take one molecule of nitrogen gas, 3 molecules of hydrogen gas, and they will make 2 molecules of ammonia. And then the molecules of ammonia can say, well, we can split apart and go back to our starting materials, the reactants. And so sometimes a reaction inside the container is this. 1 N2, 3 H2s make 2 ammonias. But then sometimes 2 ammonias will just react to make 1 nitrogen gas molecule and 3 molecules of hydrogen gas. And at equilibrium, the forward and reverse reactions happen at the same rate. Okay, so that's a reversible reaction. I forgot to cut and paste the physical states. These are gases. So over here, titled this chart here, we actually do have the equation written one more time. It's this. Okay, now let's do some experiments and actually get some numbers. So experiment number 1. Let's put in some nitrogen gas. 1 molar. What's that M stand for? Well, in a previous video, we just introduced the idea of concentration. So let's review it here. Concentration is usually measured, usually measured in units of moles per liter. So if you have a small container, that's supposed to be a little flask, like you saw on ice a minute ago, or you have a big container, the concentration can be the same. If this is a light brown color and this is a light brown color, the concentration is the same. What we're saying is, for a given liter, like maybe this is a liter and this quantity is a liter, if you count up all the moles of the gas in that liter, they'll be the same. Same concentration, kind of like density. The same number of molecules per liter. It's going to be same in the little flask, same as the big flask. And that's nice because then you don't have to worry about, oh, what's my value of the number of molecules if my container, the size of the container changes. No, so concentration is a nicer measurement of quantity than actual, hey, there's 5 grams here, there's 0.7 moles. No, let's measure concentration, number of moles per liter. Okay, So now it doesn't matter how big or how small a container is, whatever the container size, for every liter, remember this script M, italicized M means moles per liter. So we're saying, hey, if you have a 1 liter container, let's put in 1 mole of nitrogen gas. If you have a 10 liter flask, put in 10 moles so that the concentration still is 1 mole per liter. And do the same thing with the hydrogen. Seal it up, wait. You might have to throw in a catalyst, get the reaction going. In fact, I think you do. Don't put any ammonia in there initially. And let's see what happens. Come back a day or two later, check. And this is what the final concentrations will be. It's a reversible reaction. Back in the good old days when we only knew about one-way reactions, we might have analyzed this like so. We would say, hey, the recipe says 1 mole of nitrogen. We should have put in 3 moles of hydrogen to try and totally make 2 moles of ammonia. And then we would say, who messed this up? They only put in 1 mole of N2, but they should have put in 3. They only put in 1 mole. And we'd say, we're going to run out of the hydrogen gas, right? We should have had 3 moles, we only have 1. This is the limiting reagent. And if the reaction goes to completion, if it was a one-way reaction, we should use up all the hydrogen, and we're going to have some leftover N2, right? So we needed 3 moles, we only had 1. It's all going to get used up, and there'll be some leftover N2 gas, and we'll make some ammonia. Cool, but there should not be any hydrogen. It was limiting. It should have been all used up. Come back later. Hey, there's still hydrogen gas. Well, maybe the reaction's not done. Let's come back next week. It's still at 0.763 moles per liter. Let's sit a month, a year. It's still at the same quantity. It's reached its balancing point, its equilibrium. Technically, it is a limiting reagent. According to the recipe, we don't have enough hydrogen gas to react with all the nitrogen gas. But more importantly, it's a reversible reaction, which means as you make the ammonia, NH2, sometimes 2 of them pair up and go back to starting materials. And it reaches this natural balancing point where 0.921, whoa, that's pretty close to 1. It's like very little nitrogen gas ultimately reacted. And 1 went down to 0.763. Yes, some of the hydrogen reacted, and we got a little bit of ammonia, 0.157 moles per liter. That's something. That's weird. Okay, let's try it all over again. Experiment number 2, clean out the flask, completely empty it, put in pure ammonia gas in the catalyst. 1 mole per liter of ammonia gas, seal it up, come back later, and now we reach a new balancing point. Not all the ammonia disappeared, went backwards, right? We're trying to do this reaction, I guess, by starting with fresh ammonia, while you guys go and make nitrogen and hydrogen gas. Well, they made some. 0.399 moles per liter of nitrogen, 1.197. Okay, that's quite a bit. There's still some ammonia left over. And if you watch, the ammonia do break down the nitrogen and hydrogen, but at the same time, at the same rate, at equilibrium, the nitrogen and hydrogen are reforming ammonia. It's going back and forth. But what's interesting is that this number for nitrogen is different than this number for nitrogen. In fact, all the numbers are different. It's a weird new balancing point, and it all depended on how you started the reaction. Okay, so case 1 is where we put in all reactants. Case 2, put in only products. Case 3, let's just have a little bit of everything. And again, we're not really following the recipe. We're saying, hey, let's put in 2 moles of nitrogen. I don't know why, they just did. Put 1 mole per liter of hydrogen, 3 moles per liter of ammonia, seal it up with the catalyst, let it reach equilibrium, its natural balancing point, and here are the values. And again, these numbers are all different from those numbers. What's going on? Well, if we do a more detailed analysis of kinetics, rates of reaction, it has to do with the fact that the forward reaction is going the same speed as the reverse reaction. And there's equations you can write that look something like this over here. If you want to know in detail how this relationship comes about. We can talk about it outside of class. The bottom line is some theory went into this, some math, and here's the outcome. If, yeah, let's just go here. If you look at a generalized reversible reaction of this form, where you have molecule A plus molecule B making molecule C and D, and then there's numbers in front of it, the little AB, to get a number that doesn't change, you take the products. So up here on the numerator side, the top part of the fraction, we have products, and you raise them to the exponent. The exponent is the value of the number in front of those molecules. It's the coefficients of your balanced equation. And your reactants, well, you put in their concentrations. That's what the bracket means. So how many moles per liter of molecule A do you have? Raise that number to the power of your coefficient. These are the reactants on the bottom. And you get this number called K, capital K, called the equilibrium constant. It's a number that doesn't change. Okay, so let's talk about this reaction where we have one molecule N2, 3 molecules of hydrogen making 2 molecules of NH2, 3, NH3. Let's write this expression. Oh, and there's a name for it. Scientists love naming every new idea. It's called the equilibrium expression. So K, the equilibrium constant, equals products divided by reactants. Products on top, reactants on bottom. So our product is NH3. Put in brackets and take that 2, and now it's a power of 2. It's ammonia squared. Divide this number by the reactants. Well, there's the quantity of nitrogen gas. There's a 1, invisible 1 in front, so now there's an invisible power of 1 here. Multiplied times the quantity, the moles per liter, of hydrogen gas raised to the power of 3, because in the recipe, the chemical formula, sorry, the balanced chemical equation, there's 3 hydrogens for every 1 nitrogen. And so that's this number here. That's the equilibrium expression. We have a match. Sorry. There we go. And now for for the first experiment, we said, okay, experiment number 1, we put in this certain amount. Once we reach the equilibrium, the balancing point, these were our final equilibrium concentrations. So let's put that into the equation here. So we got K equals NH3 concentration. Well, that's 0.921 squared divided by the nitrogen concentration. Well, whoops, I'm getting my reactants and products mixed up. I should have written this. It's products divided by reactants. Let's not mess this up. Products is the NH3 molecule. This is our product, right? These are the reactants. Sorry. Products. The product concentration is 0.51. It's 0.157. That's the NH2 molecules concentration squared. And now the reactants are N2, and the quantity of N2, the quantity of N2 is right here, 0.92121. And there's a coefficient 1, so that's the power 1. And then it's the other reactants, hydrogen gas, H2, 0.763. 0.763. And there's a 3 in front of this balance equation, 3 here. So now it's a power of 3. If you get your calculator out and do the math on this, round it off the 3 significant figures, this is the number you get. That's the value of the equilibrium constant. And then start all over with this set of data. The equilibrium expression is products, 0.203. Balance equation, there's a 2. There it is. There's a 2 in front of the ammonia molecule, so square it. Divided by the quantity of N2, 0.399, times the quantity of hydrogen gas, 1.197. And there's a 3 in front of that. So make this cubed. Crank out the math on your calculator. You get the same constant. Well, that's why it's called a constant, because it doesn't change. And then do the same thing down here. For this experiment 3, our final values were 1.82 squared over 2.59 to the first power and 2.77 cubed. Do the math on that and boom, same constant. Awesome. So there are tables of equilibrium constants for reactions. And it's really cool because given this number, which is constant, no matter how you set it up, if you know 2 of these concentrations, you can then measure the third, which is awesome because if you're trying to make ammonia, which experiment, 1, 2, or 3 is going to make the most? Well, you get 0.15, no, 0.2, it's a little better. Oh, 1.8. This is the reaction. If these are your only choices, do this one. And if someone said, well, your final concentrations are these 2, how many of this can you have? You can use the equilibrium expression, the value of K, the value of the other reactants, and you can calculate the quantity of the missing compound. Guess what? That's what we're going to do in our homework. Let's see, did I forget anything? I think I got everything here. All right, let's try it again. Oops, move this out of the way. Okay, so we had this reaction here with NO2 becoming N2O4. So let's write the equilibrium expression. So I start off with products divided by reactants. That's always true. And then here, well, look at the balance equation. The product is N2O4. Put it in brackets to say, well, we need the moles per liter, the concentration, and it's nowhere to be found. So this is as far as they want us to get. There's a 1 coefficient, so there's a power of 1. We're good. The reactants is just the NO2 molecule. Place in brackets saying, hey, I need the molar concentration, moles per liter. Ooh, there's a 2 here, so I need a 2 here. And we're done. That is the equilibrium expression. Nice. Ooh, we got some important notes here. And I should have spread this out. Can it all fit in the screen? No. Let's shrink it so it will fit. Sorry. So here's some notes. If K is greater than 1, then products are favored at equilibrium. Or in other words, there's more products. If the products are favored, there's more of them than reactants. So if K larger 1, more products. Or we say products are favored, more products. And then if it's the reverse, if K is less than 1, then the reactants are favored, and there will be more reactants than products. Okay, so some of you might be good at memorization. You'll say, oh yeah, if K is greater than 1, I'll just remember its products. If you're not sure, one thing you definitely need to memorize is that the equilibrium expression puts products over reactants. So if you remember this, then you can figure out, hey, should K be bigger than 1 or smaller than 1 if I want more products? Well, the equilibrium expression really is just a big fraction. So pick your favorite fractions. I don't know, is it 3/8? Is it 7/214? I don't know. But here's the idea. Let's put 1 over 100. Is that less than 1? Yeah, that's 1/100th. How about we put 100 over 1? Is that less than 1? No, that's more than 1. That is 100. If you change the decimal, maybe that's easier to see that 1/100th is less than 1. But look at the ratio. If you say that the ratio is 1 to 100, this is less, K is less than 1, right? 1 over 100 is less than 1. What you're really saying is that for every one product, there's 100 reactants. And if your K is equal to 100 over 1, then you're saying that you have 100 products every time you have one reactant. Oh yeah, you have a lot more products than reactants. So that's kind of what I do. I say, I just kind of remember products over reactants. And if I want more products, just make sure the top number, if you want more products, the top number needs to be bigger than the bottom number. And if you divide a big number by a smaller one, you get a number larger than 1. Okay, so that's important to know. I'll explain why in a minute. The other important note is that if K is really big, and you talk to different scientists, they have different ideas of what a big K means. That's why it's perhaps 1,000. Well, if K is 1,000, it's like 1,000 divided by 1, which says for every one reactant molecule, you have 1,000 products. Okay, 1,001 ratio, you're pretty close to being completely done. You've taken almost all the reactants and converted them all to products. If at the balancing point you have 1,000 products in there and only one reactant on average, yeah, it's mainly products. You can approximately say it's a complete reaction. But again, it turns out that nearly every chemical reaction, even ones we think of as going to completion, might be considered partially reversible in a tiny amount. Cool. Ooh, and here is a really important note. So in addition to understand just key concepts about equilibrium, the equilibrium expression, how to calculate the equilibrium constant, products divided by reactants, you got to remember this detail. Solids and liquids do not appear in the equilibrium expression. That's because the equilibrium expression has concentration, moles per liter, and the moles per liter for a liquid or a solid don't change. Even if they're being used up, their concentrations do not change. So here's here's a little graphic to try and get that idea across. Suppose we start with a whole bunch of solid and some of it dissolves. So you got a whole bunch of it here. It dissolves to a smaller quantity. And then let's see if I can copy and paste this over here. So this amount right here is approximately how much is over there. So let me ask you, what is the concentration of solid? Well, the concentration is the number of moles for every liter. So let's say that this circled amount is equal to 1 liter. And now just count up how many molecules are in there. So you start with a huge crystal and it shrinks and reacts to a small one. Well, what's the concentration here? Well, if I circle the same volume, it's a liter. And if you count up the molecules, it should be the same number of molecules within this amount, within this volume. Or in other words, the concentration is not changing. Even though the overall numbers are reacting, they're decreasing, the solid's dissolving or reacting away. But within the solid, the concentration of molecules within the solid isn't changing. There's a certain amount, number of moles per liter, no matter where you are inside this crystal, this quantity of solid. Okay. And you do the same thing with pure liquid. Any region of the pure liquid has the same number of moles per liter of that solvent molecule. Okay, so when we write equilibrium expression, leave out the S and the L molecules. They do not appear. You only use gases and aqueous. Those are quantities that can change, right? So if you have a highly pressurized gas molecule, you have a whole bunch of circles in here. This is a container of gas. And if it's pretty low pressure, maybe you only have a couple of molecules of gas in there. Yeah, so the number of moles per liter is going to be really small here. Number of moles per liter here is going to be really large. And of course, if you talk about making a weak cup of tea, there's only a little bit of caffeine in the solution. You have an espresso, a lot, a very strong concentrated cup of coffee. There's a whole bunch more caffeine per liter of solution. It's much more concentrated. So aqueous compounds and molecules and ions and gaseous things, they can change their concentration. So they show up in the equilibrium expression. Cool. All righty. I think we got some sample problems now. So let's enlarge the page. This should fit now. Okay, so let's write the equilibrium expression for this equation. Equilibrium expression. Oh yeah, that's something equal to K. Well, it's supposed to be products divided by reactants. So K equals, well, what's our products? We have the Na2CO3. Ooh, but it's an S. Doesn't show up. There's also CO2 as a gas, so put CO2 in brackets. Find out how many moles per liter of carbon dioxide per liter is at the equilibrium point. And then times the water, wait, that's a liquid, so don't include that. So in our equilibrium expression, the products that we list are only gases and aqueous things, so only carbon dioxide. Reactants, it's this thing. If it showed up, I'd raise it to the power of 2, but it's a solid, so you don't list it. Instead, this is not 0, because you can't divide by 0. No, it's a 1. In other words, the solid concentration doesn't change. It's a constant 2, so we'll just choose to use 1 for it. Or you can simplify it and just say K is equal to the carbon dioxide concentration, and we're done. Anything divided by 1 is that thing, right? So there you go. That's the equilibrium expression for this chemical equation. Another sample problem. Suppose the following reaction, this one here, is at equilibrium, so it reaches its balancing point. And at the balancing point concentration of the CH4, what is that? That's a reactant. It's equal to, so the quantity of CH4, put in brackets, what's the concentration? Well, it's a crazy small molecule, small amount. 3.4 times 10 to the minus 33 moles per liter, tiny amount. And at the balancing point equilibrium, the C2H2, a product, is equal to 1.5 moles per liter. Compared to this one, 1.5 is a huge number. And then the equilibrium constant is 2.8 times 10 to the 66. Ooh, it's huge. Are reactants or products favored here? This number is much bigger than 1, so the products are really, really favored. Oh wait, and that kind of makes sense then. With such a huge K, it's almost a one-way reaction. It's really making a ton of products. There's very little reactants. K is huge. We expect products to be favored, and then they are. C2H2 is a product, 1.5. CH4, methane, is a reactant. It's a tiny number. Very, very little reactants left over once it reaches equilibrium. The question is, how much hydrogen gas is here? Okay, well, what we do is write the equilibrium expression. That's going to be products over reactants. So K equals products. The C2H2, that's, well, let's show all my work. How about that? So the equilibrium expression is C2H2, coefficient's a 1, so this is a 1. Hydrogen gas, that's the other product. Ooh, there's a coefficient of 3, so I need to cube this, raise it to the 3rd power. Reactant, that's CH4, and then there's a 2 here, so I need to raise it to the power 2. Okay, now we'll put in some numbers. The K is equal to 2.8, so K equals 2.8 times 10 to the 66, huge number. C2H2, that's 1.5. C2H2 is 1.5. Hydrogen, I don't know. You could change this to an X if you want. I'm just going to leave it with brackets, and you have to keep the cube there too. CH4, that's a tiny number. That was 3.4 times 10 to the negative 33 quantity cubed. Cool. All righty, at this point, if this was an exam question, you've earned all your points except for 2. You're gonna get 1 point for doing the algebra and 1 more point for actually finding what the hydrogen H2 concentration is. I might give you like 3 or 4 points for writing this correctly, you know, a point for remembering to put the exponents there, a couple points for setting up, you know, properly identifying what number goes in what spot. But at this point, it's not chemistry anymore. This is a math problem. So let's just crank on the math. What I might do first is square this. Yeah. And if I want to show all my steps, you don't have to on the exam, but show me a few steps so I can follow your math, give you partial credit. If you make a mistake, if I find it, it's like, oh, that's only a half point off. But if you were to just jump and show me the final answer and it's not right, then I can't give you much partial credit. So on the exam, show me some work so I can give you some partial credit if things go sideways. Let's see, 3.4 times 10 to the minus 33, punch that in the calculator and square it. I got 1.156 times 10 to the negative 65. Okay, and then I thought maybe I'd take 1.5 and divide it by this number. 1.5 divided by that, I got 1.297, a whole bunch of digits. I rounded off to 6. So remember when we dealt with significant figures, you're not supposed to round off to the very end? Well, the shortcut then is to keep a lot of digits, more than what you need. So then when your rounding error won't be so bad. So how many significant figures should we report in our answer? Let's go back up to the question and take a look. 3.4 times 10 to the minus 33. The 3 and the 4 are sig figs. There's 2. 1.5, 2 sig figs. 2.8, 2 significant figures. Yeah, everybody's got 2 significant figures. And we are multiplying, dividing. The rule is the term with the fewest sig figs determines the number of sig figs in the answer. We should have 2. So if I carry 5, there should not be much of a rounding error. So it's okay to round off. As long as you don't round off too little, don't round it off to 2 sig figs yet. You'll definitely get a rounding error. Okay, I think I've finished my algebra so far, right? 1.5 divided by that crazy number is this one. Now we have to divide both sides by this number. And what did I get? I got 21.5783, and again, I rounded off, this time to 6 sig figs, just to protect myself. I know at the end, I'm only gonna carry 2. And then what you need to do is find the cube root function, or you can raise, so you need to take the cube root of 21.5783, or your calculator can have the power button. Sometimes it's a caret, you know, that little thing, to the 1/3 power. That's equivalent to taking the cube root. So if you have a cube root function on your calculator, take the cube root of both sides, the 1/3 power of the cube root, they cancel out. So now you have the hydrogen gas concentration, and the cube root of 21.5783 is well, my calculator spat out a number like 2.784 with some other digits, but I'm only going to keep 2 sig figs. So 2.8. And what's the units? Brackets mean moles per liter. The capital M is a symbol. for moles per liter. There we go. 2.8 moles per liter. There's one last thing I forgot to do, I just remembered, and that was looking at K and deciding whether products or reactants are favored. So I think we already did this one, but real quickly, is K bigger than 1? Yeah, 10 to the 66 power, huge number. Products are definitely favored. So if you look at the reactants, tiny number. The products, 1.5, and then we just found 2.8. Those are big, big numbers compared to this little number. So yeah, definitely products are favored. If we look at these numbers here, K, is that bigger or less than, larger or smaller than 1? Well, the exponent's to the -2 power. It's smaller than 1. If you multiply this out in your calculator, your K will be 0.0602. Get it out of scientific notation. Just put it in the decimal. Now it's a little easier to see. Yeah, it's less than 1. So reactants are favored when K is smaller. So how does that compare? Well, the reactants are the N2 and H2. Look at these numbers. They are bigger than the product. How about for this other one? N2, H2 are reactants. Yeah, these two numbers are both bigger than the products. And this last one, here's a reactants, 2.5, 2.7, both bigger than 1.8. Reactants are favored. Cool. All righty, that's enough for now. Get some practice in the homework, and I'll see you in the next video.